In this segment, we're going to take a look at one of the very important properties of a fluid, and that is the viscosity of a fluid. So what viscosity does is it relates the local stresses within the fluid to the amount of strain or shear that is occurring within the fluid element itself. And what we'll begin with, and it's a very common approximation to be making with fluids, we will assume that the fluids that we're looking at are Newtonian. And with that, that means that the shear stress, we define shear stress with tau, is proportional to, and what we'll show in this segment, it will be proportional to the strain rate within the fluid. And this typically holds for common fluids that we often deal with. And examples of those would be water, oil, or air. There are other fluids that we'll talk about in a later segment that are non-Newtonian, and for those, this type of relationship would not hold. But when we look at this, if you recall back, if you've taken a course in solid mechanics, this relationship looks a little bit like Hooke's law. So it looks a little bit like Hooke's law that you would see in a course in solid mechanics. However, the difference here is that we're looking at the deformation rate. And if you remember from one of the earliest segments in this course, we talked about the difference between solids and fluids was that when you shear a solid, it only deforms through an angle, whereas when you deform or apply a shear to a fluid, it will continue to deform. And so that was the difference between a solid and a fluid. And consequently, we see it within the equation that we're going to derive here. So what we're going to do, we're going to start with a little element of fluid. And so imagine we have a chunk of fluid, it looks something like this. And what we are going to do is we are going to assume that there is a shear stress. Well, first of all, let's define the axis or the size. So this chunk of fluid is delta y in the vertical, and it is delta x in the horizontal. That gives us the size of the chunk of fluid. And then what we're going to assume is that up here we're applying a shear stress, and that shear stress is going to be shown to be proportional to the deformation rate of the fluid itself. And what we'll do, we'll derive an equation for that. So let's assume that we apply this shear stress. What will happen is the fluid element itself is going to deform, and it'll look something like that. And this would be at a later point in time. And assume that the velocity at which we're deforming at, let's say it's u, and I'm going to denote that with a delta u. And in a given amount of time, the fluid element itself is going to deform through a certain angle, and we'll call that angle delta theta. And over here we will have a delta theta as well. So delta thetas are the same. And we know if the fluid element is moving at a speed of delta u, and let's assume that this takes place over a period of time delta t, we can then say that this distance of this deformation is going to be delta u, that's the velocity that it's displacing, multiplied by delta t, or that time. And down at the bottom, what we're going to assume is that the lower chunk of the fluid element is fixed. So it is attached to a wall, and we'll call that the no slip condition. We'll look at that in a later segment, but for right now, let's just say that it is attached to the wall and it's not moving. So we can use geometry to write out an expression here. So what we have, we'll use trigonometry. We have tan delta theta is equal to opposite over adjacent. So that's delta U delta T divided by delta Y. So we come up with an expression or an equation, and what we're going to do, we're going to impose the small angle approximation. And so in doing this small angle approximation, we're going to assume that all of the deltas go to differentials. And so it will be a differential sized, a very, very, very small displacement in angle or in velocity. So let's take a look at that. If we make the small angle approximation, the previous equation then becomes this. And I've done a little bit of rearranging. I've moved the delta t to the left-hand side of the equation, du dy. So if you look back with the small angle approximation, we had something like this, delta u delta t over delta y, and all I've done is I've taken this and I've moved it down there, and I've converted the little differential elements into the d for a differential equation. So with that, if we look back to what we were saying in the earlier slide, that shear stress is proportional to delta theta by delta time, what we have here is that the shear stress, if you recall that, we can say it was proportional to d theta by dt. Well, we see from the equation, from this little chunk of fluid, what we have is shear stress is then equal to du by dy, which is coming from this equation up here. I'm bringing it in. But there needs to be some sort of constant of proportionality. And that constant of proportionality that we use in fluid mechanics is called viscosity. And so we put the viscosity in there. That gives us the constant of proportionality for this relationship. And what this does is it gives us the force. Actually, it's stress, but assuming it's over a unit area. So the force due to shearing from velocity. So if you shear a fluid, this would be the force that resists that shearing motion. And mu in here is a constant of proportionality. And that is the viscosity. And it actually turns out that this is what we call the absolute viscosity. We'll look at another form of viscosity called the kinematic, and it's basically this divided by the density, but we'll look at that later. So let's take a look at this now. So we have this equation. We have, we have tau. Tau is equal to mu du by dy. Let's take a look at the units in this equation. Now, tau is a shear stress. So the units of shear stress is going to be newtons per meter squared. And on the right-hand side of the equation, we have the units of mu. For right now, I'm going to leave it unknown. And then we have it multiplied by a velocity divided by a distance. So velocity we know is meters per second, and distance we know is meters. So consequently, what we can do is we can rearrange this and try to isolate and determine what the units of the absolute viscosity are. So if we expand this, the meters cancel out. We have newtons seconds per meters squared. Newtons, if you recall, F equals ma, force is equal to mass times acceleration. We can expand newtons as being kilograms times meters per second squared, and then that's multiplied by seconds per meters squared. We have some cancellations that are going to occur there. That goes, that goes. So what we end up with for the viscosity is kilograms, and it's divided by second meter or meters second. And so essentially what we have are units of mass divided by length times time. So those would be the units of viscosity. And you'll see different units in different books, but really it could either be that or it could be that for the absolute viscosity. Now, one last thing that I should say, and I did mention this at the beginning, this is assuming that we're dealing with a Newtonian fluid. And the characteristic of a Newtonian fluid is that tau is a linear relation of du by dy. Now there are some fluids that are non-Newtonian, and for those fluids it is not a linear relationship. So you would have a nonlinear relationship here. Those are fairly complex fluids to analyze, and we will not be analyzing them in this course, but I will give you some examples of non-Newtonian fluids in the next segment. So what we've looked at here, we've covered the viscosity of a fluid. It's a very important parameter or property that we will be using in all of our analysis.